Hey folks, time for a bit of a break. Momentum. So the next two lessons, we can forget about vectors except for directions in a straight line, forward and backward, okay? Um, Momentum is kind of a neat concept. In fact, it's how Newton originally did his laws. He actually didn't do it as F equals ma. He actually developed it from inertia first. So momentum is basically a quantity of inertia. So, because any object in motion has a property called inertia that makes it want to resist its motion. In fact, that's what your mass really is. It's not to do with your weight, it's to do with your inertia. A heavier object will resist the change much more forcefully than a lighter one. So what Newton did is he combined an object's mass with its velocity into something he called quantity of motion, which is what we refer to now as momentum. So momentum is quantity of motion. By the way, the symbol for momentum is rho. Um, it's a P sort of a script. Technically, it should have a little half arrow on top of it, but again, we're not going to worry about that because online it tends to turn into this, the square, which doesn't really help you. So rho, momentum, is mass and times velocity. So the momentum, the unit is kilogram meter per second. M is the mass in kilograms, V is the velocity in meters per second. So kilogram meters per second. I may have made a mistake on a few of the future slides with putting a square there. Please ignore it if I did. So, for example, let's say you've got a car that's 1,000 kilograms moving at 15 meters per second east. Its momentum is just 1,000 times 15, so it's 15,000 kilogram meter per second east. Mass is a scalar, so it won't change the direction at all for you. So easy to find momentum. Now, how momentum changes, he actually didn't write it as F equals ma. He first stated that the rate of change in momentum was proportional to the net force applied, that it was proportional to something called the impulse. So he originally wrote it actually as this, that F times delta t is delta p. So, by the way, you're going to see what we're going to do. Delta basically means, every time you see a delta in math, it means final minus initial. It means change in. Now, what we're going to do is to show, because we're going to have sometimes multiple objects, I can't use rho 1 and rho 2 to be the first and the second velocity. So what we're going to do is we're going to put a little prime signal after it. So basically just like just a little asterisk or something not an asterisk, just a little slash after it, just to show this is the one after, because we are going to have multiple objects very soon when we start doing collisions. So I can't use rho 2 for being the final anymore. So I'm going to put a little prime symbol. This means the final momentum. That's the initial momentum. So that F times delta t he called the impulse. So, and that's actually kind of interesting. It said that there's two things that are important. One is the force. The second is how long the force applies for. So we could get the same impulse from a big force applied for a short period of time, or a small force applied for a very long push. So this is what's called the impulse. So whenever you see me ask for impulse, it's force times time or change in momentum. You can find it two ways. The nice thing about impulse is we could use that to calculate what the effect of a non-constant force is. So if we find the area under the graph of force versus time, that actually gives us the impulse. Or we could find the impulse at certain purpose points and just add it all together. This is kind of a very simple version of what you're doing in calculus. Is finding the whole point of calculus was to find the area under the curve. That's why he invented calculus. To solve these problems. I shouldn't do these before I've had my coffee in the morning. Now, so if you get it up, that means it's an increasing force. Triangle down means decreasing. A level, a square means it's a constant force. So we can use that with calculus now to find the impulse for any curve. So this is actually how we really do physics, is we basically, if something's hitting it, let's say we have something hitting a golf ball, a person is applying a force to a golf ball where you have a contact beginning and ending and it sort of deforms a little, then you have maximum compression, then it shoots out. We can actually use this with the impulse to find very precisely for any shape of force what the force is going to be. And this is actually what you're going to do next year. This is why we're teaching you calculus, why you're suffering, is to be able to find a solution like this. We're not going to do one like that in this class, but just letting you know that's why we do it. So the use of impulse and momentum can be really good. We can find change in momentum because the change in momentum is the momentum after minus the momentum before, which is mv2 minus mv1, or rho prime minus rho, mv prime minus mv is the way I'm typically going to write it. Then we know the impulse is the change in momentum, which is also mv2 minus mv1. So we can find the change in momentum also from the impulse. So, for example, let's say you got a 40-kilogram child sitting on a 40-kilogram wagon, and they're pushed by a force of 75 newtons for 2 seconds. You want to know what their change in speed is. To find that, normally we'd have to actually use F equals ma, we'd have to solve net force, then we'd have to plug it into acceleration. The nice thing about this is you do it all in one step. It's a lot faster, a lot cleaner. So write out what you know. The mass of the kid is 80. The force is 75 newtons for 2 seconds. I want to know what their final velocity is. All right, well, the impulse, force times time, is change in momentum, so it's final minus initial. So it's mv prime minus mv, which is 0 because the kid's at rest. Plug it in. 75 times 2 is 80 v1. Solve. The kid's moving at 18 meters per second forward. A little faster probably than you want your child to be going on a wagon. So that's impulse. It's really, really actually quite easy to do. I'm not going to spend a ton of time chatting with you about it because what it does is way more important than the math. The math is actually, you're going to find the easiest thing we've done in this course so far. You just plug in a force, a time, and an initial and final velocity, and you'll solve for one thing that I haven't told you. All right. If I ask you just to solve for the impulse, you can either solve for this or you can solve for that. They're both the impulse, depending on what I give you. All right. Good luck, everybody.